Hey,
Yeah, there
good
they're
to
in.
see you again, Doug.
Hey, at some point, do you want this with you? This is the deed, which we're going to do.
Yeah, we can
a
do
little
that.
flourish.
Great. Welcome, everyone. I'm Dan Lewin. I'm the CEO of the Computer History Museum. I'd like to welcome you all here today. I'm with Andrew Feldman, who's one of the co-founders of Cerebras, and we have some exciting news today to share. This is a groundbreaking moment, both for the museum and for the industry. We're here to accept and receive and talk about the wafer scale engine, which is a breakthrough in wafer scale compute technology that is going to and is revolutionizing the frameworks for artificial intelligence. So Andrew, welcome.
Thank you for having us.
This, to put things in perspective, as you can see, the wafer scale engine is a dinner plate sized wafer. But the more interesting thing about it is not the size of the plate itself, of the wafer itself, but rather the fact that it houses 2.6 trillion transistors and 850,000 optimized cores that are tuned for AI kinds of applications. So this is really a transformational moment in the industry, and as we think about the future, we'll have to hear a lot more from you and your company in the years and months to come, so thank you. We will be presenting and putting on display the wafer scale engine here at CHM. And to put it in context, the thing that I'm very excited about is at CHM in the last few years, we have changed and transformed our mission and purpose. We're focusing the museum on decoding technology, the computing past, the digital present, and the future impact on the human condition. And obviously, AI is all about augmenting the human potential that we have in the world. And computing, for those who remember and can think back long and far away, computing in the beginning was a person. A person was a computer. And then we invented these wonderful things, these tools. And now, for the first time in history, we have a wafer scale engine that is going to bring new technology and new applications to the world. It's also important, I think, to reference that as a history museum, we're really not about the past. We're about the present, having a conversation with the past. And I'm going to have a conversation with Andrew that really talks about the thinking that went into the creation of this company and this product, which is really, and he'll be the first to say it, I think, standing on the shoulders of giants that came before, but also to offer up a perspective that Andrew has offered about the museum, is that it's kind of the Hall of Fame for things that have had breakthroughs in the industry. So thank you for saying that about the museum, and we're happy to accept your product into the museum. So Andrew, maybe you'd like to offer a few words to kick off our conversation today.
You know, when we started Cerebras, it was Gary Lauterbach and Sean Lee and Michael James and JP Fricker and myself, and we were meeting in a upstairs little conference room that some venture capitalists lent us, and we just wrote two things on the whiteboard. That we wanted to work together again. We'd all worked together previously, and we wanted to change an industry. And we wanted to change this industry. We care about it. And we wanted to put our shoulders against it and see if we could move it forward, see if we could have an impact. And for us, this is the Hall of Fame. And we walk around your collection, and we know people who worked on the things here. We remember them from our youth. We remember trying to fix that Walkman over there. Those orange headphones that came with it, and little fluffy things that fell off all the time. For us, this is sort of a place where our people are recognized, the people who build things and use this technology to create. And it's such an honor. I've told now hundreds of employees that, you know, when we started the company, our goal was to be here.
Well, we're glad you're here. Could you talk a little bit about your thoughts in the very beginning relative to the application and use cases for this type of technology at this scale? I mean, we are talking about, you know, almost, it's hard to envision the notion of 2.5+ trillion transistors. we were chatting earlier, one of my earlier experiences was in a company that was doing breakthrough work where we were building a little chip that had 25,000 gates in it, and there was one company in the world that could even build that chip. Now, look what you've done.
Well, first, I think the honest truth is it's Gary and Sean and Michael and JP and the teams we built. I think I'm no tech visionary. I think, you know, you asked me earlier how we arrived at this, and it's because Gary lied to me and told me it wasn't that hard. And he said, yeah, and compilers aren't that hard either. And that's just not true.
Right.
What the team saw was that this workload was different. Mm-hmm. That this workload required a tremendous amount of communication across chips. And that the best way we could think of to reduce latency, reduce power, increase bandwidth, was to not cut up the wafer. Mm-hmm. You know, usually we take a wafer and we cut it up and we test each part and then we put it in a box and then we buy another box to tie those together, right? So we break Humpty Dumpty and then we spend all this money trying to glue it back together.
Right.
And our view was that imagine what would happen if you didn't. Mm-hmm. And it took an extraordinary amount of effort and creativity. And years of work and hundreds of millions of dollars of invested capital and investors who were patient and believed in us.
Right.
And I think that's a magic combination: extraordinary founders and big ideas and investors who let founders dream big.
Mm-hmm. Yeah, you truly have to suspend disbelief to go after a problem like this.
Yeah, you know, nobody is sitting back saying, you know, for 70 years, the entire history of the computer industry, everybody who's tried this has failed. Why don't we do it? Right. I mean, that's sort of what we did. And one of the great joys of being in the Valley is you can surround yourself with fearless engineers.
Yeah.
People who take that as a challenge. Yep. And who are attracted to problems that other people can't solve.
Who were the first customers that you were interacting with? Because clearly you had to be thinking about the application space and the way these machines would be put to work and this architecture would be deployed.
You know, some of the few advantages, Daniel, of getting older is you know more people. Yeah. And so, you know, from previous companies, we had relationships in the supercompute space. We had relationships with pioneers in computing and supercomputing like Rick Stevens at Argonne Labs. We had relationships with leaders at Google and at Facebook and at collections of different companies who were struggling with the problems of AI. And all the problems sort of were, when distilled, were the same thing. It took too long to train models. Mm-hmm. But this was holding us back. The models weren't big enough, and it took too long to train, and that was a compute problem. And when we unpacked it, it was a problem of communication. Mm-hmm. And so when we thought about sort of where should we target our energy, which part of this problem should we invent against, mm-hmm. the problem of communication sort of was first and foremost. Mm-hmm. And that's why we ended up with wafer scale. And many of those first customers who were the first to sort of provide feedback, and they're often sort of missed in the storytelling, mm-hmm. right? The role of these groups of real leaders on the user side who right. make time to talk to inventors and entrepreneurs and to share sort of their problems mm-hmm. are often overlooked.
Yeah, and that, I mean, all things considered in this notion of artificial intelligence, defining the problem is the hardest problem, right?
There were some really hard
right.
problems, and we were fortunate both in our personal relationships and the relationships that our investors had. Sure. And the early investors were, you know, Benchmark and Foundation and Eclipse, and that continued with an extraordinary group of investors, and they had relationships too. Yeah. And so they could put us in front of people and we could distill that into an opinion that if we solved this problem, if we made a part that looked like this, we could really deliver extraordinary advantage to them.
This may be a very basic question, but I'm curious. Did you start off in anticipation of this size and scale and this particular, sort of target for your solution, or was it something that you accumulated through your interaction with the customers?
I think what we understood from the customer was that if we could make training faster, they would iterate more frequently, they would run more experiments, they would produce better results, and their ideas could take flight.
Yeah.
And what we then did, and this is something that Gary taught me years ago, is you try and ask, what does the compiled software ask of the underlying machine? It's what every computer architect asks.
Right.
You know, what is the right tool for this job? What is the right machine to do this work?
Right.
Why is this work different from other work?
Right.
And that's when we really understood the challenges of communication and memory access, and that led us to how do we put these chips close together?
Yeah.
And we experimented with ideas, and we built on sort of JP's pioneering thinking, and we tried experiments, and some worked and some were disasters, and we ended up thinking that even though everybody had historically failed at this, we thought we had a shot.
Yeah, you certainly did, and you delivered. The thing that's fascinating to me, again, sitting here at CHM at the museum, is that, and as I said earlier, this notion of connecting the dots, looking from the past forward, there clearly was a roadmap of attempting to do these kinds of things for years, but the perseverance, the timing, the technical aptitude, the skill, and the perseverance to pull this together at this moment in time. Were there any bumps in the road where timing was off for you, or?
This has been just a smooth ride. It's easy as pie.
That's what I was thinking.
Every idea we had has worked
it all
perfectly.
Worked from the get-go.
Perfectly. We've been under budget and ahead of schedule from day one. I mean, I think this is good stuff.
So tell us about one of the trials that you ran into that you flattened with a SWAT.
I think I think when you look at successful people's LinkedIn, you're fooled by this collection of successes.
Yeah.
And it's not a truth. And when you look at a successful engineering project, it's the same thing, that it's the result of effort and failure and learning and setting that aside and then trying again. And when you're done and you retell the story, you organize it in this set that looks like a successful lineage, right? And we tried many things that didn't work. And I think if you're going to do fearless engineering, you have to be prepared to be in an engineering cul-de-sac and to back out and to laugh at yourself a little bit and to say, all right, what did we learn? How do we back out? Let's take a new step and try another set of experiments. And this is true on the hardware side and true on the software side. And I tell people a sort of an anecdote that if you were the first people to climb Everest and you were sitting at base camp with this group that had just failed, and you're having a beer, and they say, it's really hard, there's a spot about halfway up and it's terrible and it's going to kick your butt and you're going to have to come down, and you gulp and you say, okay, and you go up and do it then. You come back down, you're having beer with the same guys, and you lean forward and say, that spot halfway up, it's not the hardest. And we got to parts that nobody ever got to. Others had failed way earlier than we had. So the problems that we were encountering had never been encountered before. The problems of trying to put these materials together, not just to make it, to yield it out of the fab, but to package it.
package
to
it,
deliver power to it,
power,
to cool
heat
it,
dissipation,
to write software to it,
Right.
to write a compiler that's spreading work over hundreds of thousands of cores.
Right.
These were problems that we had, that nobody'd ever attempted, let alone solved. There was no received wisdom.
Right.
And then when you do this fearless work, when you do sort of deep tech, you don't have sort of a catalog of components for your vendors to help you with.
Right.
Right. Usually, when you need a heat sink, you go to a catalog and you pick one, or you call the sales rep and he shows you 3, and you choose one and you go. And when you say, well, you know, we're at about 18 kilowatts and it's 46,000 square millimeters, and then they say, you know, you smoking dope? That's a wafer. That's not a part. Nobody's ever built a part. So at every stage, it takes this sort of discipline and engineering methodology where. You know, we'd never even bought a whole wafer before. So the first time we were shipped wafers, we didn't know how to ship wafers. We ended up with a box of broken glass, right? A box of shards. All right, got to learn how to ship. And so we called up TSM. How do you ship a wafer?
Right.
And, well, actually, there's a board and there's a way to do it, and a box. And now we know how to ship wafers.
You know. Right.
And each time there was these learnings that went away, and you had to sort of keep this amazingly sort of upbeat attitude, and you have to believe in the process. And here, you know, Michael James and Sean are sort of helped us with sort of course we can do it. I mean, of course we can do it, even when you're sort of down that this particular set of experiments didn't work. You know, sort of a fierce creativity that say we're nowhere near our list of experiments.
Yeah, it's fascinating. I'm curious, you know, the packaging, from my understanding, of course, has always been a big issue along the way in this industry, semiconductor industry, and then heat dissipation. Do you have a sense of obviously the benefits? Because as we think about these cloud-based services and hyperscale computing in general, that's been, blossoming over the last 15 or 20 years. I believe that the calculation is that now, roughly speaking, about 2% of the world's energy is going into these compute data centers. It's a stunning percentage when you think about it, that it's actually a number, a whole number. What are the benefits on that front? Because again, this is an area where we start to think about the new problem space, because you've created a paradigm shift.
Right.
Right. It's a real paradigm shift.
We have in packaging used to be cool. And people doing material science PhDs used to think about going to the semiconductor industry in the US, and we shipped those jobs elsewhere. And it went with the fabs. And this sort of unbelievably important part of taking a piece of silicon and turning it into a working thing, delivering power to it and enabling others to put it on a motherboard. Right. Delivering I/O to it. We shipped off, and we looked for partners, and we couldn't find people to do it. And so we did it ourselves, and we invented along the way, and it wasn't easy. I mean, I can tell you we cracked a lot of wafers.
I'll bet.
Right. And we put them in an oven, and we tried to figure out what was happening with the coefficient of thermal expansion between the cold plate and the main motherboard, and cracked another wafer. And like, this is our 63rd wafer we've cracked.
Yeah. It's just...
And what do we learn? All right, you go back and you think about it, and we had to sort of become experts in thermal interface materials, in flexible connectors that manage shear. And these were things that I think when we began, none of us were experts in. And later, when we talked to experts, that they were awed at what the team knew.
No, I can imagine. I asked the question at a fundamental level. I'm years removed from it, but I remember those being the fundamental problems and the issue
These are hard problems
of shipping away a lot of the talent.
But I think one of the really sort of fun things, and the co-founders can share with you about being an engineer is not doing the same stuff you did last time. Is you have a methodology to solve an amazing collection of problems. And you can choose to apply it to problems very similar to the ones you did last time, or an entire range of new problems. Yeah. And what was sort of so wonderful about the collaboration among the founders is sort of, for me anyway, is watching fearless engineers sort of go to work and make themselves experts. Yeah. They didn't begin experts in wafer scale. Nobody was an expert in wafer scale. And we weren't experts in packaging, and we weren't experts in compilers of this size, and over years and real work, and we are now. And that's really, it's an amazing thing.
It is. It's fascinating to listen and learn about the journey you were all on. Can you, if you can recall, kind of the last hurdle that you had to jump as a team?
So everybody told us well, we're not over the last hurdle, right?
Well,
so you know,
you will be setting hurdles out in front of yourself for a long time.
Is a business hurdle, and as a startup, we've got a lot of ways to go.
Sure.
But we are through the technical risk.
That's what I'm getting at.
The last technical risk was sort of this realization that everybody told us that yielding out of a fab would be hard. And it took us about $20 million and a year and a half, and we solved that problem. And then we were in uncharted waters, how to package it. And that took us $200 million in the next 2.5 years. And the problems that we encountered around sort of affixing 3 different materials together that move differently when heated, right? You use a copper alloy for a cold plate, and I'm just parroting stuff JP taught me, but you use a copper alloy for cold plate, and that moves a ton. And you're going to run water on the backside, so you're trying to cool it. Yeah. The silicon barely moves, but your main motherboard is somewhere in between. It's fiberglass, and it's going to move some. So you've got this sandwich, and each of the 3 layers is moving differently. Yeah. And that took a long time, and just patience, and sort of a doggedness, and a relentlessness from the team, and faith in your colleagues that this problem would get solved. Yeah.
I love the way you describe this. It's so consistent with the purpose of the museum to help our audiences understand as we decode, the problem space and the way technology, is changing the world. And in your case, if we move beyond kind of the technical hurdles, of course, there will be other hurdles you'll create for yourselves, whether it's responding to markets.
We can find hurdles.
You'll find hurdles. You guys are good at that. But I'm curious, maybe we can shift a little bit and talk about the workloads, the kinds of things that you're seeing in terms of the application space where customers are engaged and what kinds of problems they're trying to solve.
I think 10 years ago, AI was a nothing. Yeah. Right. I mean, maybe credit card fraud. It wasn't the #1 class at Stanford, right? What?
Well, we were doing search, and there were some real basic machine learning things.
That's right. There was some regression and logit and probit, and
very horizontal.
That's right. It wasn't deep learning, and the guys who are now fathers of the field were in obscure places, writing in obscure journals. Right. And today, my 90-year-old mother-in-law asks Alexa to play Frank Sinatra. And Alexa puts together a playlist that includes songs she forgot she liked. Right. Right. And she can then tell stories about when she first heard this. And our 8-year-old granddaughter goes to Netflix, and Netflix is picking cartoons for her. With an AI, and when you've got the under 10 and the over 90 demographic, you've got a pretty good chance of impacting how society lives and how they work and how they play. And when you get in the car, your phone's going to tell you if the way you usually go home isn't the best way, and that's an AI. And if you take the search engines out of our lives, and you take all these things that sometimes you know and sometimes you don't know that it's an AI background. If you removed that, our work would be very different right now.
Right. There are some target areas, though, where, from my understanding, some of the, the science-oriented and discovery-oriented things for healthcare and other parts of the modern world where, we need to live and learn at a faster rate if we're going to solve the problems. I mean, I'll speak, again, given the nature of the museum and the fact that we're all standing on the shoulders of the giants who put things in this, as you call it, Hall of Fame. The original supposition that Doug Engelbart had in creating kind of the modern desktop computing and communication world that we know was we were causing problems for ourselves as humanity that were going to require the collective intelligence of humanity to solve. Individuals couldn't do it. Now, you brought together a team that cracked a pretty big nut and created a pretty interesting wafer scale engine here. It's going to optimize these machines to learn quicker, faster, and better for some discrete problems that are going to change society in many ways. What do you think about that?
First, I think that as infrastructure builders, we know that others are going to put their ideas on our computer, right? And whether you're building switches and routers, whether you're building computers, whether you're building roads, as an infrastructure provider, you have to love the fact that other people will use your ideas to make their ideas fly, right? And so our first customer in its first application had the largest data set of drug interaction and its impact on tumors for cancer.
Awesome.
And found things that nobody had ever seen before. That's our very first customer. That's not a better fitting t-shirt.
Right.
That's important too, but the very first customer in a very first application used it to attack a problem that impacts us all.
Yeah.
Sort of how to better control tumor growth with medication.
Yeah.
We have a customer right now who's used our system in combination with other systems to model COVID, and it's the best COVID model. We have other customers who are, just staying in the healthcare field, are synthesizing all known research on a given field to help their researchers stay abreast of all research in any language. We have still different customers who are using our system to more efficiently search for oil. To still other customers thinking about how you could modify the behavior of a combustion chamber in a coal-fired power plant to be more efficient, to reduce pollutants by changing the mix of gases that are allowed in. Right?
That's amazing.
These are fundamental problems.
Yeah.
And we take great sort of pride that as infrastructure builders, that other people sort of ride on our roads to new places.
Yeah.
Right? That they get to solve problems that they previously couldn't solve.
Yeah.
That their ideas take flight with the help of our equipment.
Yeah, it's fascinating. We were talking about this earlier, just the notion of over time generations, 10, 15-year clusters of those who've been in the industry for a long time, seeing what this next generation of problem solvers, these young PhD students and others who are looking at problems in a new and interesting way, and how this platform and this tooling and this engine is going to give them a new set of techniques where they can live and learn, in a matter of days, which might have taken months, and those months would add up to too much time for them to solve their problem in their learning, right? So, I mean, there's just an accelerated learning process here that's very exciting across so many different fields.
What we've learned for sure in software has probably taught us more than anything is iteration is your friend.
Yeah.
And a system like ours, built on the wafer scale engine, the work of the now nearly 400 engineers at Cerebras, what it fundamentally does is it reduces the time it takes to iterate.
Yep.
And what we know is that when you can test more ideas in a short period of time, you're likely to stumble across a good one sooner.
And you solve more problems.
And you solve more problems.
That's right.
And,
No,
and that's what we do.
Yeah, it's very exciting. Also, we had a chance to talk the other day about this at a moment in time going back now probably 20, 25 years or so. I remember being at an event. These days, one of the noted venture capitalists in Silicon Valley, Mark Andreessen, made the comment about how software is eating the world, if you will. At this event 20 plus years ago, I think Mark was probably a student then. Grady Booch, who was the father of this modeling language that is kind of fundamental in building software, was given an award and was waxing on about the importance of software. And then following him was Gordon Moore from Intel, who came up and smiled. He was a very cheerful man, friend of the museum, as is Grady. He was a trustee. And Gordon kind of smiled and laughed, and he said, well, software is really interesting, but it has to run on something.
We are that thing. No,
and here's that thing.
That's right.
It's amazing.
We are that thing, and we're happy for the software community to eat the world as long as they're running on our hardware.
As long as they're running on your stuff.
That's exactly right. Exactly.
So anyway, what a pleasure and an opportunity to welcome you, your company, your end product, and this story to the museum. I would like to take a moment with you and for our audience to have the signature process by which we accept this wafer scale engine into the museum. And it comes with a deed and the provenance. You built it. You're giving it to us.
We are.
So if I could ask you, that would be delightful. There's a pen for you. And I'll do the same. And we will encourage those in the audience and those that read about this over time to come to CHM. And, oh yeah, we do have 2 copies. So let me go back. Oops, my mistake. Thank you, Dad.
This is why we have handlers.
So we have, yeah, someone to tell us what needs to be done. That's always helpful. All right, great. Thanks, Andrew. And thank you to your entire team. You're very generous and gracious in passing really the compliments off to the team. And I think that's from personal experience, and I think anyone who's been part of a company recognizes, you know, it does take a team. But I'm confident that it wouldn't have happened without you. So thank you for your vision and perseverance in bringing together the team and making sure they had the resources to get the work done.
I think at the beginning my contribution was making sure they had pizza to eat while they were doing their engineering work. We should again sort of recognize Gary and Sean and Michael and JP. And I think the final thing is that when you do this type of work, and you've done it, and many people who are watching have done this, there's a real cost on your family.
Oh, yeah.
And we should recognize our families who are here and sharing this with us. You know, these problems consume us.
They do.
And we're probably less good husbands, and sometimes less good fathers than we wished we were, and it takes tremendous patience.
Yeah.
To be married to entrepreneurs.
Yeah.
And I think our success is their success too, and we want to thank you guys.
Yeah. Well, thank you. That's not a confession. That's just a true statement.
That is the truth.
And it's one of those things that, again, I'll go back to the history of this museum, which is really the definitive institution of its kind, with a collection of 150,000 or so objects, of 1,100 oral histories of the pioneers of this industry. And, you know, a fundamental statement that I made 4 years ago in coming here and speaking to the trustees when they asked me if I'd be interested in running the museum, you know, and my statement was, you know, in the beginning, people were computers. And look what we did. And this museum is a representation of all that work, of all of those people. And there's a cost associated with it, but like any tool, computers can be put to work for good and for bad. anything that can be used at scale can be weaponized. But with these kinds of target new platforms, I think the greater good of computing will accelerate the greater good for the human condition, which is what we're hoping for. And I was really pleased to hear some of the stories that you offered about the target uses of the platform, but also you helped decode the problem space that your team came together around to overcome huge obstacles to make this fundamental breakthrough for the industry. So we're glad to have you and welcome you into the museum.
We are proud to be here.
All right.
And thank you for having us.
All right, great. Thanks so much. Right.